Going to Mars is one of humanity's greatest adventures. It's a journey that pushes the boundaries of our technology, our courage, and our imagination. For decades, we've dreamed of setting foot on another planet, and now that dream is closer than ever before. Imagine strapping into Starship, feeling the rumble of engines beneath you, and blasting off from Earth, leaving behind everything familiar. The countdown echoes in your ears as you and your crew embark on a voyage that will take you millions of kilometers away from home. After months drifting through the vast emptiness of space, you finally see the rusty surface of Mars growing larger in the window. The descent is tense, but at last you touch down on the red planet, making history with every step. But once you're standing on that dusty ground, a crucial question hits. How do we get back home? The excitement of arrival quickly gives way to the sobering reality of the return journey. Getting home from Mars is an even bigger challenge than getting there. The distance is vast and the risks are enormous. Every decision matters when your life depends on it. Earth is a moving target, orbiting the sun at incredible speed. Launching off Mars at the right time, flying for months through deep space, and re-entering Earth's atmosphere safely takes enormous energy and precise planning. You need a lot of rocket fuel to escape Mars's gravity and cross millions of kilometers of space. Every kilogram counts, and every drop of fuel is precious. If we had to pack all the fuel for the round trip from the start, our rocket would be impossibly heavy. The more fuel you bring, the heavier your spacecraft becomes, making it even harder to launch. The more fuel you carry, the more fuel you need just to lift that fuel. It's a vicious cycle that quickly becomes unsustainable for interplanetary travel. So, what if Mars itself could provide the ingredients for our ticket home? Imagine using the planet's own resources, like water ice and carbon dioxide, to create rocket fuel right where you land. This is the key to making humanity a multi-planetary species, learning to use local resources to survive and thrive. Building the technology and infrastructure to live off the land on Mars is essential for long-term exploration and eventual settlement. Solving the return journey puzzle is the first step in turning science fiction into reality. It's not just about getting there, it's about coming back and doing it again and again, until Mars is no longer a distant dream, but a new home for humanity. Our first Martian explorers need a safe, reliable way back to Earth. Their journey home will pave the way for future generations, opening the door to a new era of exploration and discovery. What powers a giant rocket like Starship? It's not just brute force or sheer size, it's a marvel of engineering and chemistry working together to overcome gravity and reach the stars. Unlike your car, which runs on gasoline, Starship relies on a special mix: liquid methane and liquid oxygen. These aren't just any fuels, they're chosen for their efficiency, storability, and the possibility of making them on other planets. Methane acts as the energy source, while oxygen is the oxidizer, absolutely essential for burning fuel in the vacuum of space, where there's no air to help the process. This combination creates a controlled explosion, generating the immense thrust needed to escape Earth's gravity. When you mix and ignite them, the result is a spectacular burst of energy that sends Starship roaring skyward, leaving a trail of fire and ambition behind. To make this journey possible, a single Starship needs about 1,200 tons of fuel just to launch from Earth. And for the return trip from Mars, it needs a similar amount, fueling up for a round trip across millions of kilometers. But carrying all that extra fuel to Mars isn't practical. It's like trying to hike across a desert with a week's worth of water strapped to your back. The extra weight would make the journey nearly impossible. That's why the plan for a sustainable Mars colony depends on making fuel after landing. Instead of bringing everything from Earth, we use what's already on Mars. Mars must become our gas station, a place where we can refuel and prepare for the journey home or even further into the solar system. If we can reliably produce hundreds of tons of methane and oxygen on Mars, it changes everything. Suddenly, Mars isn't just a destination, it's a launch pad for future exploration. With this capability, we could create a permanent outpost complete with a reliable transportation system shuttling people and supplies between Earth and Mars, opening the door to a new era of interplanetary travel. The key to all of this is turning Martian resources, like carbon dioxide from the atmosphere and water from the soil, into rocket fuel. This process, called in situ resource utilization, is the foundation of sustainable space exploration. That's how we make the round trip possible. by transforming Mars into the ultimate travel snack stop for humanity's journey to the stars. Space planners call it ISRU, in situ resource utilization, using what's already on Mars to survive. Early explorers brought tools, not lifetime supplies. We'll do the same on Mars. The most important thing to make? Rocket fuel. The plan land a fuel factory on Mars before any humans arrive. This automated plant works for months, producing the methane and oxygen Starship needs for the trip home. Mars's atmosphere is thin but 96% carbon dioxide, perfect for extracting carbon and oxygen. Methane is CH4, 1 carbon, 4 hydrogens. We get carbon from the air, but where's the hydrogen? The answer: water ice, buried beneath the Martian surface. Mars has vast amounts of frozen water, especially near the poles and in the soil. Water's formula is H2O, hydrogen and oxygen, just what we need. So, Martian air gives us carbon and Martian ice gives us hydrogen. Together, they're the ingredients for making rocket fuel. That's the ISRU dream. Using Martian air and water to make fuel sounds great, but getting water on Mars isn't easy. The water is locked as ice mixed with dirt, like a frozen, muddy puddle. Extracting it would require landing heavy mining equipment, excavators, drills, loaders, all needing to work perfectly after a 9-month journey. Remote operation is tough, with signals taking up to 20 minutes to reach Mars. Martian dust, wild temperature swings, and dust storms make everything harder. Even after digging up the ice, you need to heat it, collect the vapor, and condense it back into water. This process is complex, energy-hungry, and full of potential failures. For the first missions, relying on unproven robotic mining is a big gamble. The first astronauts will have enough challenges. Adding risky mining could jeopardize the mission. We need a simpler, more reliable way to make that first return trip certain. What if we skip Martian mining and just bring the water with us? We already know how to store and transport water reliably. By bringing our own water, we avoid the risks of complex, untested mining equipment. Starship's huge payload capacity makes this possible. We'd need about 400 tons of water. Heavy, but much less than the 1,200 tons of finished fuel. The plan lands Starship with water tanks and a chemical processing plant. The factory simply plugs into the water tanks. No excavators, no drills, no soil ovens. Fewer moving parts mean fewer things that can break. This approach makes fuel production predictable and testable on Earth before launch. For the first Mars missions, knowing your ride home is fueled by a simple, reliable process is a huge comfort. It's the safest trail for our first explorers. Once Starship lands on Mars, carrying its precious cargo of water tanks, a new chapter in interplanetary exploration begins. This is where the real chemistry begins, literally and figuratively. Creating fuel on Mars is a blend of science, engineering, and a bit of ingenuity. We start with 2 essential ingredients: water brought from Earth and carbon dioxide, which is abundant in the thin Martian atmosphere. First, we use a process called electrolysis to split water into its basic elements, hydrogen and oxygen. This process is powered by solar panels, harnessing the energy of the sun on the Martian surface. The oxygen produced is carefully stored for use as rocket fuel and for life support. Next comes the Sabatier process, a clever chemical reaction named after the French chemist who discovered it. Here, hydrogen from the split water reacts with carbon dioxide from the Martian air, passing over a catalyst to produce methane and more water as a byproduct. The methane is then stored as fuel for the return journey, while the extra water is recycled back into the system, making the process highly efficient and sustainable. It's an elegant, closed-loop system, recycling water and pulling carbon directly from the Martian air. Over the course of several months, the storage tanks gradually fill with methane and oxygen, building up the reserves needed for the Starship's return flight. By the time astronauts arrive, their ship is already fueled and gleaming on the Martian surface, ready for the journey home. All of this happens autonomously, while the crew is still safely on Earth, giving mission controllers confidence that everything is ready for human arrival. This method is not just efficient, it's been tested and proven on Earth, and can be fully validated before any crew ever leaves the ground. It's the technological magic that makes a round trip to Mars possible, and it all starts with the simple act of bringing our own water. Bringing our own water slashes complexity and risk. Fewer machines mean fewer chances for failure. No mining robots, no drills, no soil ovens, just tanks, pipes, and a chemical plant. The system is controlled, self-contained, and much easier to manage. As soon as Starship lands and deploys solar panels, fuel production can begin immediately. No waiting for mining or scouting locations. The water is ready. The faster we make fuel, the sooner we can greenlight the crewed mission. This approach shortens the mission timeline and reduces hardware exposure to Mars's harsh environment. Reliability is everything in human spaceflight. By choosing a simpler method, we trade extra launch weight for a much higher chance of success. For our first Martian pioneers, that's the most important promise. Of course, bringing water to Mars has its own challenges. Water is heavy, and every kilogram launched from Earth is expensive. Carrying hundreds of tons of water means less room for other supplies. The trade-off, more launch mass for less risk on Mars. For the first missions, safety outweighs cargo capacity. As we gain experience, future missions might combine water carrying with small-scale mining. Another challenge: energy. Splitting water and making methane requires lots of power, so we'll need large, robust solar arrays on Mars. These must work in weak sunlight and survive dust and temperature swings. So, while the water carry plan is simpler, it's not easy. It's a pragmatic, step-by-step approach. Solve the return trip first, then tackle bigger challenges. We build a bridge to Mars, one reliable step at a time. Packing our own water does more than solve a technical problem. It makes Mars safer and more achievable. The first Martian astronauts will be true pioneers, facing unknowns with a secure ride home. With a fully fueled Starship waiting, their mission is a round trip, not a one-way gamble. They can focus on exploring, doing science, and adapting to Mars, knowing their lifeline to Earth is secure. This approach paves the way for a sustainable outpost and eventually, a settlement. Each cargo ship brings more supplies and each return trip becomes routine. Step by step, we expand humanity's reach into the solar system. Imagine being one of those first explorers, stepping onto red soil with your return ticket ready. This isn't just a dream, it's the future we're building now. The journey to Mars is our next giant leap, and by solving the return trip, we're ready to stick the landing.